Hello everyone. Today we're going to be talking about isolated systems, conservation of momentum, and impulse. What is an isolated system? An isolated system is one that can be separated from the surrounding environment. And what that means is that the important conserved quantities, like momentum, are conserved in this isolated system. In other words, we've already included all the important elements. For instance, if we look at you riding on a skateboard and you have some initial velocity, if we just consider you riding on your skateboard, we couldn't quite consider that an isolated system because we know that as you continue down the road, there'll be some distance at which you'll stop. And so there's another important element in you on your skateboard, and that's the friction between the wheels and the sidewalk. So in order to make an isolated system, we now have to include the friction because you do come to a stop. So we're going to consider a few more systems. We're going to point out what is this isolated system, and then talk about how momentum is conserved in these situations. All right, so the next thing I'd like to talk about is impulse, which is denoted by the letter J, and impulse is just the change in momentum, so the final momentum minus the initial momentum. So let's take a look at this video and then talk about how the Hot Wheels momentum changes. Alright, so in this video we had the Hot Wheel car coming down the ramp, and then now where we're concerned about is this interaction with this wall or this book here. So this Hot Wheel comes along with some velocity, and then after it collides, it comes back with nearly the same velocity. So I'll just go ahead and show that to you again. Alright, so what is the impulse of this car? Let's say that its velocity is about 2 meters per second, right here down at the bottom, and its mass is about 50 grams, or 0.05 kilograms. So at first it comes and it's moving to the left, so let's just call the left is minus x, so that's going to give us a minus velocity. And then after the collision, it's moving to the right. So P final is going to be m, which is 0.05 kg, times this, it's going to the right, this 2 meters per second. And so we're going to get 0.1 kilogram meter per second. P initial is the same mass, 0.05 kilograms, but this time, since the velocity is going to the left, that's got to be a negative 2 meters per second, so minus 0.1 kilogram meter per second. So then now we can calculate our impulse, which is the change in momentum, so P final minus P initial. And so we're going to get 0.1 minus a negative 0.1, so we're going to end up with 0.2 kilogram meter per second is the impulse on the car during this collision. So here we have the red car starting off on the ramp, and it's going to collide with this purple car. So after this collision, the red car continues moving, and then the purple car moves even faster than the red car does, whereas the purple car was initially at rest. So in these two videos, so let's work out how fast the purple car is moving. Here we have the red initial is equal to 2 meters per second. And we have the purple initial is 0. The purple car is initially at rest. The red comes down the track and hits it at this 2 meters per second. We know that m red is about 2 m purples. So what we know is that during this collision, momentum is conserved. So that's P initial is equal to P final. So here we have P initial is going to be equal to m red initial, m red, times v red initial plus m purple, v purple initial. Now since v purple isn't moving initially, that's just 0. So here we could go ahead and plug in what this m red is in terms of mp, just so that we have one less quantity to think about. V red initial, and here we can even plug in that. So here we have 2 times 2 meters per second, so that's 4 m purple. So now we can think about what our final momentum is. So that's m red, v red final, plus m purple, v purple final. Now after the collision, both of the cars are still moving. So we can't just scratch off one of these two quantities. After this collision, v red is moving, let's say, about half as fast as it was initially. So when we plug that in, m red is 2 m purples, and now it's moving half as fast, so that's 1 meter per second, plus m purple, v purple final. And this is what we want to find out. So now what we can do is we can equate these two to each other and then solve for this v purple final. So here we have 4 mp is equal to 2 mp plus mp v purple final. So let's get rid of those mps. That's pretty tedious. So now we have 4 equals 2 plus v purple final. So let's subtract off that 2. So we get 2 is equal to v purple final. And this is in meters per second. So now let's go back to the light car moving down the ramp and hitting the heavier red car. So in this video, we have the purple car is moving at 2 meters per second right here before the collision. And the red car is at rest. And again, we have m red is 2 m purple. So our initial momentum is going to be m purple, v purple initial plus m red, v red initial. M red initial is just 0. So our momentum is going to be mp times this 2. And again, we're going to be looking for this final momentum. And so in this case, we have v And now let's consider what we need to know to find the final momentum. So here we have Vp final is 0, and V red final is something that we want to find out. So our final momentum is going to be M red, V red final plus M purple, V purple final. So we can go ahead and plug in this 2M purple, V red final, plus this was just a 0. And now we can equate these two to each other because we know that momentum is conserved. So here we have 2 mp is equal to 2 mp Vr final. So Vr final is equal to 1 meter per second. In this problem we have 3 carts that all collide at the same time. Here we have initial momentums, and here we have final momentums. So what is the momentum of the system before the collision? So P initial is going to be this 5 plus minus 1 minus 3. This is just going to give us 2 kilogram meter per second. So what is the final momentum after the collision? This is minus 4 plus 2 plus 3. This is also going to give us 2 kilogram meter per second. So now we can ask, is this an isolated system? What we know is that the initial momentum is equal to the final momentum. So yes, this is an isolated system. Here we have a load of coal dropped from a bunker onto a railroad hopper car. So let's draw this out. So now we have this railroad car moving, let's say, to the right, and then after some time this railroad car now has this load of coal dropped onto the car. What is the inertia of the load of coal? Okay, so a few more pieces of information. One is that the mass of the car is this 4.010 to the 4 kilograms. We know the initial velocity of this, that's 0.5 meters per second. And we know that after the collision, so this is V final, is 0.3 meters per second. And we know that the coal and the car are moving together. So what is the initial momentum? That's going to be this 4.0 times 10 to the 4 times 0.5 meters per second. So this is going to give us 2.0 times 10 to the 4 kilogram meters per second. So that's our initial momentum. And we know that our initial momentum is equal to our final momentum. So then our final momentum is equal to the total mass of the system. So that's going to be the mass of the car plus the mass of the coal. Both of them start with C, so that's unfortunate. Times V final. So what we want to know is this M coal. We know this V final. So let's go ahead and set these two equal to each other. So here we have this 2.0 times 10 to the 4 is going to be equal to this M of the car, V final, let's multiply them out, plus M coal, V final. Here we know this V final, that's this 0.3. So what we're going to do is do this 2.0 times 10 to the 4 minus the mass of the car, V final. And then now we have M coal over on this side, so we're going to end up dividing by V final. And what you'll find out when you plug this in, you should get something like 2.7 times 10 to the 4 kilograms. Here we have a cannon. Alright, so here's our cannon. It's going to fire a 30 kilogram ball at 60 meters per second. The cannonball and the cannon are sitting here and everything is at rest. So that tells me pretty easily that our initial momentum is 0. That's fine. So then after the collision, or explosion. The cannon is going to shoot back this way, it's going to recoil, and the cannonball is going to be ejected this way at 60 meters per second. So in order to conserve momentum, the cannonball goes this way to the right, the cannon recoils to the left. So in order to stop the cannon from flying back too fast, we need to add sandbags. So how many sandbags need to be added for us to limit the recoil velocity to this 2 meters per second? Alright, so our initial momentum is 0. Our final momentum is something that we want to know. So let's work that out. Final momentum is, let's do the cannonball first. We know the mass of the cannonball. Let's make cannonball B, since these both start with C again. Alright, mass of the cannonball times the velocity of the cannonball plus mass of the cannon times V of the cannon. And then the cannon is going to move with these sandbags, so it better have the same velocity. So this mass of the cannon, the velocity of the cannon and velocity of the sandbags, let's rewrite that to be mass of the ball, V ball, plus mass of the cannon plus mass of the sandbags times V. And this V is what we want to set to be this 2 meters per second. So now we can set these two equal to each other. So we have 0 is equal to M cannonball, V cannonball, plus mass of the cannon plus mass of the sandbags total times that V. That's that 2 meters per second. So in order to solve for this mass of the sandbags, we need to bring the cannonballs over to the other side. So we get minus MB VB is equal to mass of the cannon V, I'm going to multiply this out, plus mass of the sandbags V. So I want to find this mass of the sandbags, I need to bring this also to the other side. So we're going to have minus MB VB minus MC V, and then now I can see that V is just mass of the sandbags is over on this side, so I got to divide by a V in order to get MS. So there's one more important thing here that we've kind of neglected, and that's what is this V? So we said V is equal to 2.0 meters per second, but we need to note that it's going to the left. So this V is actually minus 2.0. Since we called the 60 moving to the right positive, this guy needs to be a negative. So when we plug this in, we need to plug in a minus for that V. And so what we're going to get is we're going to get about 400 kilograms. So then if you want to know the number of sandbags, we just divide by the mass of each sandbag, and you're going to get about 10 sandbags we need to load up onto this cannon in order to keep the velocity pretty small.